Welcome to the 32nd session on operating system and Linux. I'm Manibhushan D'Souza, and in today's class we are going to look at thrashing. In particular, we are going to look at what causes thrashing and how to use a locality reference. And then we will see two of the model like the working set model and the page fault frequency to handle the thrashing problem. So let's first look at what is thrashing. Then we will be able to figure out how to solve this problem. Now let's look at a situation. Generally, what happens in our system is, so we know that we have a CPU that executes the processes. So we are all familiar. So CPU takes the process which are there in your ready queue. So we are all familiar with this idea. So we have the ready queue here, and the CPU takes one of the process and starts executing. This is all known. But now we also know that every process which is there here requires some frames in the memory. So there will be some frames associated with every process that is currently using or that is being used or that is there in the ready queue, because it is active, and some frames must be there for that particular process. And we also know that these frames has to be brought from the corresponding pages which are there on the secondary storage device. This is all known for us. Now let's imagine a situation wherein one of the process says, I want one page. So it tells the operating system that I want one page. So what the operating system will do is it's going to get that page over here to the memory. So it will bring that page into, or in other words, it swaps the page into the memory. But if the memory is full, you know very well, operating system will see to it that many programs are running and the memory is effectively used, as well as the CPU is also utilized to its best. So when a new page is being brought in, if there is no space, what the operating system will do is it will try to get one frame by knocking out the content over here. So that may belong to some other process. So the operating system simply goes, finds a victim page, and then tries to fill the content over here. Now this page may be required by some other process. Okay, so someone else was using that process. So this process was using that page, but what the operating system did was, because the process 1 said I want a page, it removed the frame of the process 2 and it filled that space with the content of P1. Okay, there's no problem as such. Now what if the process 2 goes and tells the operating system that I want one page, I need one page, or I need one or more page, I need one or more frames for my processing. So what the operating system will do, the operating system as usual will try to find that page, and it will try to bring in that page for that process. Now in this, during this particular process, what the operating system will do, it will knock out other processes. So that's a general thing. So it will find a victim page, swaps it out and swaps in the other process. So that's the usual thing. It has to remove one of the page. If they assume that the memory is full, don't think that this is free, why can't you put it over here? Assume that the whole memory is full, and operating system will find one of the victim page and knocks it out, then fills it with the newer page. So no problem. Now here you notice there is a chain reaction. One of the process said I want a page. Because of this, the other process page was removed and the other process started. Someone else page is removed. Now what happens is this is going to create a chain reaction. It's kind of a chain reaction wherein every process now says my page is not there. So at the end what happens is when one of the page is removed, the other page will come and the other page will say that my page is not there. So someone else gets done. So when a page is not there, let's come to this point. If the page is not there, what the operating system will do? Suppose if the process 1 says my page is not there, my memory, I have to get the page from the disk. What is the meaning of saying I have to get from the disk? Getting something from the disk is nothing but input output operation. And you know very well, whenever you tell the CPU that I am performing input output operation, CPU simply switches to the other process. So when this P1 says to the CPU that I have a input output operation, CPU, what the scheduler will do, CPU scheduler, it will schedule the other process to the CPU. What the other process is saying, I can proceed, but my one of the my page has been taken up by somebody else, so I don't have a page with me. So it will generate a page fault and it will tell the CPU that my page, it was there, my frame was there in the memory, somebody took that frame, now I can't continue. So this is again input output operation. So what happens when there is a input output operation, what the CPU will do, CPU will try to switch to the other process. So other process comes and says to the CPU, same old story, my all frames were there, somebody took one of my frame, now I can't proceed, and this is an input output operation, so you will have to wait. So CPU switches out to the some other process. So here you notice that, remember, reading from the disk or writing from the writing to the disk is all a very slow process, and we have already studied that every device will maintain a queue. Okay, we are all familiar with that. So what happens, all these processes, they are standing in a queue. So they are in standing, the process 1 is standing first, asking the disk, give me the page. Process 2 will come after some time and say, okay, give me the disk, give me the content from the disk. Process 3 will come and say, give me the content from the disk. So there are a number of processes waiting to read from the disk, and you know very well, reading or writing onto the disk is a very slow process. So all of them are not in the ready queue. Remember, whenever there is an input out operation, what the scheduler will do, scheduler will simply take the process out from the ready queue because it is not ready. When a process says my page is not available or input output operation is not required, it is not ready, it doesn't have all the resources, so it is pulled out. So what the scheduler will look at here, and the scheduler will see that, okay, this is been taken out, it is waiting for the input output, this is also waiting for input output, this is also waiting for input output, this is also waiting for the output, input output, and the CPU is simply sleeping, it's not doing anything. So CPU is simply sleeping, and you know very well the CPU scheduler is not happy with that. So what the CPU scheduler will do, it will try to load some additional programs over here. In other words, it will try to increase the multi-programming by introducing more processes. Now when the new processes comes, if more processes are coming onto the memory, they will knock out the remaining frames from here because they are being brought up, and they again will start creating the same old problem, saying that there is already, it was full, you introduced too many processes, they knocked out remaining pages, Now everybody is doing the same old thing. So what everybody is doing, everybody says that I want one page, I want one page, I want one page, I can't proceed. Everybody is queued up here, and the input output queue is full because everybody wants some pages or some or other pages to be brought in. So here you notice that CPU is not doing anything. So CPU is, when I say CPU is not doing anything, the system itself is not doing any great thing, but everybody is waiting for their pages, and this situation is called as thrashing. So everybody is being thrashed out from the CPU. What is the reason? They don't have their page. Okay, so when this happens, this particular situation wherein there is a high page swapping that is being occurring. So lot of page fault occurs. Every now and then page fault occurs, and every process is stuck. Again one process comes, page fault, again it gets stuck. So here almost everybody is doing, trying to solve the page fault problem or swapping problem, but the CPU is sitting idle, no productive work has been done. That is what is called as thrashing. So what is a thrashing? Thrashing is a situation. So it is a situation in which system is spending more time servicing the page fault. You know very well, when there is no page, you get a page fault. It's not. Than doing a productive work. What happens? A process which is in thrashing. So what is the meaning of saying a process which is in thrashing? A process that frequently generates a page fault spends most of its time trying to get the page than trying to execute its code. So this is not, it's not a good thing. Remember, if the CPU is not doing any work, its throughput decreases. If the throughput decreases, that means the system is not being put into an efficient or effective work. It is simply wasting its resources. So this thing has to be removed. Okay. So how does the thrashing occurs? I've already talked about it. Okay. So operating system always tries to monitor the CPU utilization. Okay. If there is a low CPU utilization, what the operating system will do in the multi-programming environment, it will try to introduce a more process and increase the degree of multi-programming. Okay. So what is being done? To introduce a new process, it uses a global page replacement algorithm. So what does this global page replacement algorithm will do? It will try to search a victim page. Regardless of the process, it will try to search one vacant frame, and it will fill that vacant page with the newer page that is being brought in. Okay. Now, suppose if the existing process require more page, what it's going to do? It starts page faulting. Now, when it starts page faulting, some other processes pages are being given to it. In other words, when one of the process says I want page, what happens? The CPU will allocate a page or a frame. I'm interchangingly using the word page and frame. You know the difference. So this, when it is there in the memory, it is a frame. So when a frame has been removed from the other process may come and say that I want my page. In that case, somebody else frames are being targeted. Then other process will come. Okay, and what happens? All these process which generates a page fault, saying that I don't have a page, they will go and queue up the device. Okay, that is your hard disk. Okay, and there will be empty. After some time, you notice that your ready queue is empty, and the CPU is very happy that these people are fighting on their own, and nobody is coming to me. Let them fight with the hard disk or with the secondary storage device, and let me keep quiet because there is nothing is there. So what happens is CPU utilization decreases. When the CPU utilization decreases, the CPU scheduler is not happy with that. Its work is to give more and more work to the CPU. So the CPU scheduler sees that CPU is simply sleeping. So it starts increasing multi-programming. So it says that, okay, I won't allow you to sleep. I will give you more work. So it will introduce new processes. So when the new processes comes, They knock out the existing pages, causing still more page fault. And what happens? The result is more processes will go and queue the paging device. So more and more processes will go to the hard disk or the secondary storage device and say, I want my page, I want my page. The secondary storage device says, I can't compete with the speed of CPU. Everybody has to wait. I will do it very slowly. I will give you one page at a time, but all of you have to patiently wait. So there are many processors waiting with the device, that is a paging device, and CPU is still very happy. But when the CPU is happy, the CPU scheduler is not happy, and the CPU scheduler will say, okay, I will teach you a lesson, I will add more and more processors. So it starts increasing the degree of multi-programming by introducing still more process. When more process comes, it is going to create a chaos, because there is no memory available for the existing processes. They are fighting with each other, and you introduce still more, and there is going to be a thrashing. Okay, when the thrashing occurs, what will happen? There will be a higher or a huge number of page fault. In other words, page fault rate increases tremendously. Okay, and then no work will be generated, because every process is saying that I don't have page, I don't have page, I can't proceed because there is no page or no frames as such. Again, I'm using interchangeably using the word frame and page. Page means what is there on the disk or what is there on the secondary storage. Frame means what is there in the memory. They can be interchangeably used, because most of the time the size of the frame and the size of the pages are same. Use the same size. Okay, now look at the thrashing phenomena. So if you this is general, not in a particular thing. So if you have the degree of multi-programming, what is the meaning of saying degree of multi-programming? So as the number of programs increases, when you introduce one program, degree of multi-programming is only one. If there are two programs in the memory, degree is 2, degree is 3, degree is 4. So as you increase the degree of multi-programming, that means to say that as you increase more and more number of processes. So CPU is there, CPU is idle. If you give one process, CPU is very happy, because it is very lazy. Only one work is given, it says okay, I will do it leisurely. If you give two processes, CPU says okay, I can still manage it. If you give three, the CPU say I can still manage. 10, CPU says it is a bit difficult, but I can manage. So as you keep on increasing the degree of multi-programming, the CPU utilization also increases. But there will be a time you will get a peak there here. Okay, so that is the limiting value. So after that limiting value, what happens is, if you are still eager, or if you are still wants to increase the utilization of the CPU, and if you think that okay, it's going to go and it's going to reach to the heaven, if you try to think, and if you start increasing it, what happens is, instead of increasing, suddenly CPU utilization drops. And you know very well, it drops very sharply, because after this point onwards, there is, so this is the limiting point. You notice here where the CPU actually thrashes here. So if you notice, not this one, slightly here, okay, at this point, okay, you can see that where it starts putting it down. Usually we take, you are all mathematics students, you usually take the middle value here, somewhere in the middle you take that. Okay, so at that point, anyway, at a point when it reaches the peak, above this, if you try to increase the degree of multi-programming, you will not increase the CPU utilization, rather you end up in thrashing, and the CPU utilization abruptly drops. Okay, so the CPU utilization will, oops, let me, okay, CPU utilization will go up to a maximum value is degree of multi-programming is reached. Above this, thrashing will start, and the CPU utilization drops. Okay, now how do we reduce the thrashing? So the next effect is, remember, once the thrashing enters into the system, nothing happens. So we have to say to it that thrashing does not happen. Now there is no magical spell that will stop the thrashing from happening, you can't do that. But we can think of reducing the thrashing. Okay, why we say that why I'm not saying thrashing can't be removed out, because we want more and more program to be executed at any program or any machine that you take or any system that you take it. We want to increase the degree of multi-programming. More number of programs are there, CPU will be utilized more and more effectiveness will be there. Whereas if you reduce the degree of multi-programming, everything will come to an halt. But if you are the if you want to increase the degree of multi-programming, what happens is it may so happen that it may reach the thrashing point, and after that everything may go down. Okay, so what how do we reduce it? Okay, the way in which we can reduce it is by using many techniques. One of them is by local replacement algorithm. So this is one of the easiest algorithm. In this, what we are saying is, in that particular algorithm, what they are saying is, okay, if a processor says, so this is the processor, where is my, there is a processor, there are a lot of pages associated with the processor. Suppose if these many frames are associated with the process P1, and if the P1 comes to the operating system and the P1 says to the operating system, I want one frame, then what the operating system will do is, it will not disturb the other process, rather it will try to replace its own frame. So whoever said that I don't have the page, their own frames are getting replaced. So that's a great idea, is it not? You are not disturbing other, just because initially what happened, one process said I don't have a page or I don't have a frame, or the operating system did. Operating system took the frames of other process and gave it. So it robbed the frame from the other process and gave it to this process, and the end result is you know very well. End result is thrashing. Everybody ended in a page fault. Now here what is being done is, operating system now learned that if I try to take a frame from the other process, everybody will end up in thrashing. So it says that, okay, you don't have a page, I will take your page and I will replace it with the new page. So page or frame, please, again I'm interchanging, so somehow my mind is taking the same word page, but take it as frame. Okay, so if the process says I don't have a frame, take one of its frame, not somebody else's frame, take its frame and replace it with the new frame. So in that case what happens is, only that process will end up in page fault, others will not have a problem. So that's a great idea. Okay, so it is not stealing the frames of the other processors. Okay, now the problem is, if the thrashing occurs, see there is a other problem with the thrashing which I have not mentioned to you. See, during the thrashing what happened is, let me draw that thing again. So during this there was this disk was there. I want only that part. So this disk was there which was rotating, and there is this so not this one, there is this memory was there, okay, with the frames. Now these processors came one after the other and said that I want my page, I want my page, I want my page. So many processor came, process P1, P2, P3, everybody said I have everybody generated a page fault. And you know very well, whenever there is a page fault, all of them will go to the disk and say, give me the page, give me the page, give me the page. So all these processes had a page fault. Remember, they had a page fault. That is why they are queuing. So why they are taking medicine, because they have some disease. What is the disease they have? They had a page fault disease. So they went, they had a page fault, and the operating system said, I will get you the page, wait. So they are waiting in queue because they had a page fault. But imagine there is one other process, it wanted one extra page. It has nothing to do with the page fault or other thing. It wanted to read something from the file. Okay, input to read from the file or write to a file. This has nothing to do with the page fault. But what happened, when it came to the disk said, already many people are waiting here, you go and wait after here. Already that queue is there, don't come, don't break the rule, wait in queue, come in queue, all other 10 are waiting for their page, whatever your problem, you want to read a file, write a file, delete a file, I will do it, but you come on queue. Now what is the thing over here is, those processes which had page fault, they are definitely bound to wait. They have lost their time with the CPU, they will have to wait, they have to get it. But what about the other innocent so-called the innocent processes? There they didn't had any page fault or other thing, they wanted to use the disk, but the secondary storage is busy processing the other. So what happens is the service time keeps decreasing. Okay, so on an average what happens is the service time. What is the meaning of saying service time? The service time that is required to serve a process keeps on decreasing. So, okay, and not only that, page fault also, the process which have generated page fault, their service time also decreases, because what is happening is this the secondary devices are very busy, or the so-called as a swapping device are so busy trying to fulfill the request. Okay, so how to reduce that? One of the other idea that is being used, one idea I have already told you. What is that one idea? You take the local only. So pages have to be removed from the local process only. If the process P1 says I want a page, then only P1's frame has to be replaced. You don't touch the frames of P2, because otherwise P2 will come and say I have a page fault. So don't do that. So that's the one idea. Next idea that we have here is the locality model. So this is a different idea. Okay, so what they are saying in this is, in this particular idea is, whenever you use a program, whenever you have written many programs, like you have written, like somewhere you have written int x equal to 10, you have written like this, and then you call this sqrt of 10. You call this function, let's assume that you called this function. Okay, you called this function. Okay, now what happened, this function, somewhere somebody has written this function, let's say double, and they say sqrt, and let's say double n. Somebody has written this function. Let's assume that this function is written. Inside that there will be variable. Now if you don't like this, if you say that, sir, I never studied how to calculate the square root, nobody taught me the function. Okay, I have not studied Rangekutta method or any other method for finding square root. Okay, it's all right. You have studied about bubble sorter. So if you just take the bubble sorter, how many will be there? There will be I int I will be there, int I, int j, int n, something will be there. You know that for I is equal to 1 to n, you have done for j equal to n minus 1, you have done that thing. So there will be some local variables over here, local code will be here. Okay, so there will be sorry about that. So let's look at that. You had your program, and your program called a subroutine. Okay, so in that subroutine, what happened is there are local variables, local codes, everything will be there. So when the program, or when the CPU is executing this subroutine, like this subroutine can be square root or your bubble sort, which you are already familiar, at least you have studied this one. So from your main program, so you had this main program, from your main program you called this bubble sort, and when the CPU is executing this bubble sort, all the variables, all the local variables are being used. The global variables generally are not used. Not that it cannot use, but generally we don't use the code from here. So if I declare int I here, this is the local int I. It has nothing to do with the other I or something that is declared on the main program. You are all familiar with that. So what happens is only these local variables or local code or local content are being used. So this is called as a locality. So this whole thing is the locality. Within this locality, that code is being used. Now, when I say, I have given you the example from the code, but in the memory, now just look at, let's assume that this is the memory, so this is your RAM. Generally, whenever the code starts executing from within one locality of the RAM, even though the RAM extend till here, from within a small locality, okay, the values are read, either read, written, or something within a small region. That code is being written, and that is called as a locality. So what is a locality in our case? Okay, locality is that small area. Now this small area that I have said in the RAM may contain number of pages or frame, whatever you think about it. So frame or page, they for general discussion, they doesn't make much of a difference, they are same. So if you say that within this locality your code is in this locality, then what do you mean by saying that? It may read or write into this page or frame, it may read or write to the other frame, it may read or write to the other frame. So let's say all three pages or frames are in the locality. So what is the meaning of saying locality? So locality is nothing but it is a set of pages, it may be more, one or more set of pages that are actively used together. So given process actively uses one set of pages, either 2, 3, 5, whatever it is. So within a given time it just uses them. There may be other frames which are required or other pages are required that they are not using. For example, when you do the bubble sorting, you finally output the values in the after doing the bubble sort. Remember, during the sorting, bubble sorting, that output page printf that you have written, printf with all these things, they are not required when the bubble sort is being performed. So those pages are not required. Only these pages which are currently being used, they are called as a locality. What is locality? Set of pages that are actively used together. Okay, so what does this locality model says? So there is a locality model. You know what is the meaning of saying locality. So the locality model says that during the execution, when the program executes, goes on, the locality, okay, shifts from one to the other. So locality model says that as a process executes, it moves from one locality to the other locality. Okay, is it not true? Just to give an analogy, remember this is just an analogy. So you want to come to college from your house. So you step out of the house, that's all your neighborhoods that you see. As you climb the bus and as the bus travels from one stop to the other stop, what happens? The locality changes. It may be somebody else's locality. So you see the scenery which is specific to that bus stop. Okay, and finally you reach the college. Similarly, the program executes, it will have one locality. After some time it will have other locality. Remember, locality will contain number of pages inside. It's not one page, it may be set of page. So as the process executes or moves from one locality, executes, its locality changes from one to the other. So you can imagine that a program consists of number of localities. What is localities? Set of pages which are actively used. So as the program executes, it may use one set of pages, and after some time it may use other set of other set of pages. After some time it may use other set of pages, but there can be an overlap. Remember, this set and this set, because as you transit, you know, when you go from one bus stop to the other bus stop, there is a transit. Somewhere in middle, the locality changes, overlaps. When I say the changes from one bus stop to the other, like you come to the middle of the bus stop, then it is the locality for both the bus stops. Okay, so there can be also an overlap. There may be an overlap also. There may be, not that it is always. Okay, so how do I say which is the locality? Now locality depends on how the program is written. If you have written a linear program, then the idea is different. If you have used the modular approach, it may be different. If you have used the object oriented approach, the things may be different, and again it depends on the data structure that you are using. Okay, so as I've already told you, if you are calling a one subroutine, like if you call a print the bubble sort function, then only those local variables will be used, and when you exit out of this bubble sort, those locality you are coming out. So you are going into the bubble sort locality. So you are going into the bubble sort locality. So you are in the bubble sort locality. When you come out of this bubble sort, that locality is gone. You are in the main locality. So how this is how it goes. You go from one locality to the other locality. Now let's come to the model. What does this model says? The model says very simple thing. You decide the locality of a program. So if the locality has 5 pages, see to it that all the 5 pages are there in the memory. If the locality has 3 pages, see to it that all the 3 pages are in the memory. In other words, when your program is executing, it has some locality. See to it that all the pages within that locality are there in the memory. So if all the pages are there in the memory for the given process, it will not generate a page fault. If there is no page fault, there is no chance of you getting a thrashing situation. So that's as simple as that. Okay. If you allocate less number of frames, what happens? Than what is required by the locality, the process will generate a page fault. So suppose if 3 pages are required for a given locality, and if you just give 2 frames, what is going to happen? The process will, after some time, the process will come and say that I want the third page. Give me the third page. One page fault is generated, and then once the page fault is generated, you are in big trouble, because it may end up in a thrashing. Okay, so what does this particular idea says is, this model is based on a working set model. So let's look at the locality model we have seen. Now based on that, we derive a model called as working set model. So what does this working set model does is, it uses a parameter called as delta. Remember, it's based on the idea of locality. It's based on the locality model. So it defines a parameter delta, that is nothing but a working set window. So what is this working set window? All the pages which are there for a given local reference. So a window is taken. So within this you may have number of pages. Okay. Next time one more window is taken and number of pages. So this delta that you see over here will define. So delta defines a window of active pages. Okay, so that is it, your locality. Okay, so what is there, what is the base idea? You have to examine, okay, the most recently used delta references. How many what is delta? Is a set of pages, active pages. Okay, and see to it that they are there in the memory. So let's look at a simple way in which it works. Okay, if you have a page, so remember what is being done, your program is divided into working set model, okay, which consists of the locality references. A number of pages will be there. Okay, here also number of pages will be there. Now if this is an active working set, okay, and see to it that all the active pages are there in the memory. So that's the idea. Okay, if the page is active, in other words, what is the meaning of saying a page is active? If the page is part of that working set. What is this working set? Remember, don't get confused, it's the other word that is given. What is working set? It's the locality. Okay, word is same. If the page is in the locality, see to it that it is loaded. If the page is not in the locality, remove it. So simple as that. Okay, so in other words, as the program proceeds, Remember, if you have this, if you have written a program, let's assume that you have written a program with the number of lines inside here. So you have written a program with a lot of lines of code. So you have written the code here. As the program proceeds, what happens? You will have a different working set. What is this working set? Number of, now remember, go to the RAM, there will be number of pages associated with this particular code, some variable, some int x float to y and double z, everything will be there. So that requires some memory references. So for this code there will be a working set which is there in the memory. See to it that all the pages corresponding to this code are there in the memory. Now, as the program proceeds, what happens? As the program proceeds, some of them may not be required. So, as you go down and down, some of them may not be required. So, what are they? They are non-active pages. Remove them from the memory. Okay, hope you get it. So, as the program proceeds, new pages are required. Remove the non-active pages. Okay, keep the active pages in. So if the program is in this locality or in this working set, load all these active pages into the memory and remove the pages corresponding to this set. So remove the, in other words, remove the non-active pages, or in other words the pages which are no longer being used from this set, and keep only the active pages over here. So let's give you an example. So let's assume that these are the pages being referred, okay, and let's assume that delta is 10 memory reference. So you mark 10 references. So as your program starts executing, as it goes on and on, so your program is going on, and what happens, you just take the 10 references at the time t1. So at the time t1 you take how many pages are being actively being used. So you just find out how many pages are being active. Remember, you cannot, operating system cannot decide which is that. So operating system just monitors which pages are, when I say pages are being used, which page contents are being read or written to. So it just checks. So in this case you notice that 2 is read, 6 is read, 1 is read, 5 is read, 7 is read. So how many pages are there? So in the memory, these many pages must be there. Page number 1, page number 2, page number 5, page number 6, page number 7 are required. If they are not there, then for the last 10 references, this will, one of them is not there. If this one page is not there, one among them is not there, then this is going to generate a page fault. Okay, so when the program is in this locality or in this place, see to it that working set contains these many pages. Now after some time you may be here, after time t2 you may be here. Okay, so you may be in this region. Let me draw it again. So you may be in this region. So last 10 references, take last 10 references. In this working set, what are the things which are required? 3 is there, 4 is there, 3 is there, 4 is there. So how many values must be there in the working set? 3 and 4. What you can do now is you can safely remove 1, you can safely remove 2, you can say not, okay, you can remove 5, you can remove 7 and 6. All of them you can remove from the memory because they are not required for this working set, or for this locality they are not required. You can remove them up and you can keep them. So again, for the next you can keep something else. So this is how the model will work. Okay, so what is the idea here is to decide that. So in this case what I have done is I have taken, not me, the author has taken the 10 as the delta. So last 10 references. So time is, for the last time t1, 10 references are being taken. So can I take, you may say, can I take last 2 references? Only last 2 references. Can I take 4 references? It's up to you. So the accuracy depends on the selection of delta. Delta is how many? If the working set is too small, what will happen is it will not fit the entire locality. Okay, for example, if you try to take, if you say that no, I will take only 4 here, if you just take 4, it may not accurately fill all the local references. In that case they will generate the page fault. If you take too much, what will happen, it will overlap. Okay, other variable, what is the meaning of saying overlap? Some variables which are not required are still there in the memory, you have preserved them, you said don't take it, they are active, but they are not active, they are gone, so they will not be taken up, so there will be a overlap. So too small, you may not be able to fit the entire locality. Too large may overlap. Again, if you take delta as infinite, what is the meaning of that? Everything that page the program has touched, everything will be in the memory. So you will say the first page has come, keep it, second page has come, keep it, third page, keep it, don't take any page, simply you keep all the pages. So that means all the pages of the program will be there. So in the initial, only one page may be there, after sometimes second page will come, third page will come, fourth, you will not remove any of the pages. So again, this may not be a great idea, because then you will reduce the multi-programming. Okay, now the question generally arises is, okay, how do you decide the size of the working set model? How do you decide? So I just told you that you can take I just told you here 10 were taken, somebody can take only 2, somebody can take only 4 or 6 or anything. So how do we decide that? That's one major question that the operating system has to decide. But suppose if you are able to decide perfectly, if you are able to decide, then this program is going to solve, or this technique is going to solve the thrashing program problem. So what do I mean to say is, suppose again, that is just a suppose, the operating system knows how many processes, how many working set, that is delta, is required for the process 1. If it knows it, okay, somehow it knows that, okay, 10 things are required, 10 pages are required for the process 2. It also knows how many, which one, delta, that is working set, is required for process 3, how many pages are required. What do I mean by saying how many pages are required? What is the locality? So that's the idea. So if the operating system knows what is the locality, okay, if this code comes, 3 pages must be there. If the other code comes, 5 pages must be there. If something else comes, so in other words, it knows the working set. So working set contains all the active pages. So if it knows, then it can say that, okay, for the process, let's say 1, 3 pages are required. For the process 2, 4 pages are required. For the process 3, 7 active pages are required. So altogether calculate. So total 14 are there. So totally I need 14. Just assume that 14 pages to be there in the memory. Then go to the memory and find out what is the capacity of the memory. Can I accommodate all the 14 frames here in the memory? If you can, then execute them, there won't be any problem. So if the working set of all the process can be accommodated in the memory, there is no problem. If it is not, then you will end up in trouble. So what is done is, you first find out the working set for each process, like how I have done for the process 1. You find out what is the working set. For process 2, you find out what is the working set. You summation this, you sum all of them. This is going to say what are the total number of frames that are demanded by all the processes. Now what is the next thing operating system must do? It has to check with the total demand. It has to check, so this is the demand by the processor, what is the total available frames that I have. If the demand is more than available pages, then the thrashing will occur. So what you have to do, you have to say that for some processes you have to say there is a memory is there, but not sufficient memory is not there, you cannot fit into that, don't come now, come later when the memory comes. Okay, so the idea is very simple. What is being done, the operating system will monitor the working set for each process, and it will allocate enough frames so that the frames fit into the working set size. Okay, if there is no enough frames to accommodate the working set size, it will remove the process and it will be initiated later. Okay, if the memory left out memory is more, okay, then what it can do is it can start other process. So it is simple. In sleep, the idea is like this: you have the memory here. If the working set, these are just a working set, okay, delta of different processes. If they can be accommodated, you accommodate it. If the working set cannot be accommodated, remove one of them and you say that you come later. I'll give you a chance later. Tell the one process is that you have to stop for a while because I don't have enough working set here. I will start you later. I will suspend you now, but later you can start. Okay, so that the thrashing will not occur. Suppose if there is extra space is there, introduce a new process. Same idea. You look at the memory. If the memory is sufficient, or if there are extra memory is there, you accommodate. So when in the buses, what happens is if there is extra seat is there, conductor will ask the passenger, you get in. If the bus is already full, if the passenger comes, you say don't come now because the bus is already full. Okay, so same idea here. If the working set, the operating system is looking at the working set. If it can accommodate the working set of all the processes, well and good. If a new process comes and if there is no space, it will say you wait. If the existing one asks for extra, then one of them will be suspended. So that's the idea that is being used up there. So the next idea that is being used, or the next model that is used, is page fault frequency. So this is far better than the previous idea because here we can directly control the page fault by looking at the page fault, direct control the thrashing by looking at the page fault frequency. We know that whenever there is a thrashing, there will be high peak increase in the page fault. When the system realizes that there are too many page faults are occurring, so operating system looks at it, and if there are too many page faults are occurring, that means there is a thrashing. So operating system immediately realizes that there is a thrashing. Okay, so why? Because you know very well, whenever there is a page fault, that means there is less frames are there. Okay, similarly, if the page fault is too less, if that doesn't occur, that means extra space is there and nobody is utilizing it. So the operating system can guess the two things. What are the two things? If there are too many page faults are there, then the operating system can say that there is a thrashing. So some of the process has to be removed because there is a huge contention is there. Everybody is fighting with each other for memory. So remove one or two. If nobody is fighting, entire thing is calm and quiet, that means there is extra memory is there. Nobody is using it. So introduce additional process. So if the situation is calm and quiet, introduce a new process. If there is a huge fight, remove some process. So that's the idea. So you set the upper bound and the lower bound, and it depends how you're going to take it. Remember, you will not get a situation wherein there won't be any page fault. Page fault will occur. Remember, just because there is a page fault, it doesn't mean that it will end up in a thrashing. When the page fault frequency increases, keeps on again and again, within a second too many page faults are occurring, that means there is a thrashing. Once in a while page fault occurs, it is obviously it has to occur because the processes are running. Okay, so as the page fault occurs, okay, so you check the rate of a page fault, how if within a second how many page faults are occurring. So you set the bound here, upper bound. If the page fault is going beyond this, above this value, then decrease the number of processes. If it is coming down, increase. So if the page fault is going below some value, add more processes. If it is going above some value, remove some processes. That way you can directly control. Okay, so if the page fault exceeds the upper bound, remove the processor. Okay, if the page fault reduce it. Now what is given over here is the explanation that I gave is the same thing, but I told you it in the other way around. Remember, whenever there is a page fault are occurring, okay, so what is being shown over is the number of frames. So when the page faults are going above, you remove the frames. This is the number of frames. When the page fault is coming down, you put extra frames. This is the idea that is being shown there, but the PPT you may get slightly confused. So when the page fault exceeds the upper limit, okay, so that means to say that you allocate the new frames to the process. What is the meaning of saying allocate new frames to the process? By reducing the number of processes. How can I allocate? So don't get confused. So this is when you read it, you may say that no, the explanation is exactly opposite what you are saying. This is with respect to one process. When the page fault exceeds the upper limit for a given process, you give more frames to the page to the process. When it goes beyond below, you remove some pages. Okay, I will come to that. So I just read it and I thought you will get confused. That is why I am talking about that. So let's I'll come back to this statement. What is the meaning of that? Look at one process. Now I was explaining with respect to the system as a whole. Now take one process, take one individual process, and in the individual process what you are doing. Okay, in the individual process, if one process says I want page, I want page, I want page, so in other words it generates a many page fault. Okay, so it goes, okay, you check within a second how many page fault it is generated. If it is going below the upper level, okay, you give more page to them. You say that okay, you want more page, I will give more page to that. If it goes below the page fault, you remove some pages from here. So what do I mean to say here is you monitor one process P1. Okay, you look at how many page fault it is generating. If it's generating more and more number of page fault, what is the meaning of that? It is not getting the enough page. So you give extra pages. You say that okay, you are having some problem, you can't get the pages, I will allot you some extra page. Okay, take 2 extra pages because you are generating a page fault every now and then. Take 2 extra. How can I give 2 extra? By stopping some process. Okay, I cannot generate a RAM there, or I can generate a memory, additional memory. I have to stop one process and allot it to this process. Now if I have free frames, I can definitely give it. So here the idea is you look at a process. If it is generating more and more and more number of page fault, what is the meaning of that? It is running out of memory. Give extra memory to it. You say okay, I will give you extra memory, use it, don't generate page fault every now and then. But if you look at the process and if you say that it is not generating its page fault frequency, so when you give more and more number of pages, what will happen? Its page fault will decrease. Remember, when the process does not have the frames, it will generate the page fault. So what you will do when it generates a page fault, you give one frame to it. You see whether the page fault rate decreases. If it is not decreasing, you give one more. See whether it is decreasing. No, it is not decreasing. You give one more. So as the page fault frequency increases, so here you look at the diagram. So as the page fault frequency increases, you keep on giving. So when it goes up, okay, you keep on giving more number of frames to it. Okay, so after some time what happens, so first it may be running out of some process, so you give one frame, see whether the page fault decreases, the rate decreases. You give a second one, see whether the page fault decreases. No, you keep on giving it. So after some time what happens is the page fault frequency slowly start decreasing. Why? Because it has the references. Say remember, when does a process generates the page fault? So you give 3 frames to the particular process. It says it generates a page fault. What is the meaning? There is a, it requires some extra memory. So keep one extra. See whether the page fault decreases. No, give one extra. Give one extra. After some time, what you notice is the page fault frequency decreases. It is not generating too many page fault. In that case, what happens? You remove it. Got the idea? So you, when it is it's like when it is crying, you give something. If it is quiet, you take it back. So as simple as that. So when the process is generating more and more number of page fault, you give more and more number of frames. And when the process keeps quiet, when its page fault frequency decreases, you remove them from the page fault. So you gave extra 2. Now it is quiet. Quietly remove 1. Again quietly remove 2. Again quietly remove. When you remove, what happens? Again it will say no, 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 I want page. Again it will start crying. So again the frequency goes up. So again you put 1, 1, 1, 1. So by looking at the page fault, what is being done is you can directly control the page, the thrashing. So how can you directly control? You are controlling the individual process by looking at their frequency, and you notice that this is the easiest way of doing it. Okay, here we don't guarantee that there won't be any page fault, but if the page fault exceeds, you are giving. So it is like those who need, you give them; those who don't need, you take them. Simple. So whenever a process says I want, it is in need of a page and it generates a page fault, you give them the new extra pages. And when it is very quiet, it is not demanding anything, you take back the frames from them. So this is the idea that is being used. So that's all for today. Again, if you are really interested in knowing more about it, please refer the Galvin's book on operating system. Thank you for your interest.